All right, and full disclosure with today's lesson and really this week's, mostly today's, I forgot there was no school yesterday, so I planned 4 days worth of material, but I'm going to condense it into 3 days so that way we can finish up with our last lab of the semester by the end of the week, okay? With our lab, you are going to have the opportunity to do it in your house with stuff that you hopefully have lying around the kitchen, mostly, maybe a little bit from the bathroom. And there will also be an opportunity for extra credit in case some people can't do it at home. You might be able to help them out. So keep an eye out for that starting tomorrow. But what that means is that today I'm kind of jamming 2 days worth of material into one quick 20 minutes. So I'm going to be talking a lot. Hello, Anne. But yeah, so here's today's learning target. By the end of class today, hopefully you can say this statement with some truth behind it. I can use symmetry to identify polar and nonpolar covalent molecules. Now, most of you probably can't do that right now. Understandable, because you don't know what some of these words mean. There's probably one word on this screen that most of you have never heard before, but some of them you have heard before, and so I'm going to show you how you can use your previous knowledge and put it together to talk about this concept, okay? And so we're going to start here with symmetry. So I can use symmetry, so it's important for you all to know what it means to be symmetrical. So on your pair deck, I would like you to use the provided check marks and drag them on top of any of these pictures that you think is symmetrical. Depending on how you define symmetrical, there may be some differences of opinion for one of these pictures, but we'll see what we get, okay? 30 seconds. Right, so if we look on over at the Zoom screen share, we have a pretty clear consensus on the circle and the rectangle being symmetrical, which is good. Those are the two that regardless of where you cut it in half, you will see the same thing. Okay, as a reminder of what it means to be symmetrical, you are looking for mirror images of each other. Okay, and so if the circle, you cut it in half, I see the same thing on both sides. Cut it in half side to side, same thing on both sides. My hands are mirror images of each other, meaning that if I put a mirror here, I would see the same thing on both sides. Okay, so my hands are symmetrical to each other, but my one hand is not symmetrical. Because if I cut it in half top to bottom, I do not see the same thing on both sides. And if I cut it in half side to side, I definitely do not see the same thing on the top and the bottom. Okay, and so keep that in mind when we're talking about symmetry later today. We're going to be looking at molecular symmetry. Okay, the yellow one, there is nowhere that you could cut this yellow one in half so that it looks the same on both sides. Okay, this one is perfectly asymmetrical. There is no way for it to be looking like mirror images on either side. The letter K, depending on how you look at it, could be seen as symmetrical, whereas if you cut it in half horizontally, you do see the same thing on both sides. But in chemistry, we are going to be looking for multiple planes of symmetry, which means can I cut it in half side to side, see a symmetrical substance, and then cut it in half top to bottom, see it on the side, top to bottom, okay, side to side. Okay, so that was the first part. I can use symmetry to identify polar and nonpolar covalent molecules. So most of you have probably heard the word polar before. Go ahead and type, where have you heard the word polar before? 30 seconds, please. Most common answer today, a certain method of transportation. Very good. Very good. If we look on over at your classmates' responses, we have the Polar Express, polar bears. Those are the two most common answers. Polar Arctic, Antarctica, polar ice caps, polar opposites. Keep that one in mind because it will help you, as Josh is pointing out in the chat. We have certain types of bears, Polar Express, North and South Pole, polar ice, exactly. Okay, and so most of us think of polar bears, or it seems the Polar Express, which is good because, spoiler alert, the Earth that we live on is a polar substance. Okay, it is a polar object, I should say. And what I mean by that is that it has a north pole and a south pole. And we don't just call them that because it's the top of the planet and the bottom of the planet. Who decides what's top and bottom? It more so has to do with this giant electromagnetic field that is floating around the Earth due to our core being made of molten iron, lava, whatever. And so we have a giant magnet. Basically, the Earth is a giant magnet with a north pole and a south pole, a slightly positive end, a slightly negative end, a top and a bottom. Okay. Also, you can think of it that they're different in that the North Pole, the Arctic, there's no land, it's just ice. And the South Pole, if you dig far enough, you will get to land. That is why Antarctica is considered a continent, because there is land mass under there. Okay? So good. Keep that phrase polar opposites in mind and polar bears as we move on to our discussion about polar versus non-polar bonds and molecules. Okay? I need to refresh my Pear Deck because it keeps messing up. So give me just a second. I didn't want to do that. All right, great. So we've been talking about covalent bonding as sharing of electrons, okay? But we've been assuming that everybody's best friends and wants to share evenly, but that's not always the case. Sometimes there are atoms that act like me, the oldest of 4 siblings, and when I was told to share, I made sure I got the best part. So I never really shared evenly unless I was forced to. Okay, and so that's going to be this idea of polar versus non-polar covalent bonding. The Earth is polar because it has opposite ends. If you have a polar bond, that means somebody is winning. There's an uneven sharing of electrons in that game of tug of war that is happening. Okay, so in general, as you see, polarity refers to the distribution or sharing of charge across a bond or a molecule. Think of this as a tug of war between atoms to see who wants the electrons more. There is a characteristic, a value that we have talked about briefly called electronegativity that's going to help you determine if one of your atoms is strong enough to win that game of tug of war or totally steal that electron and form an ionic bond. We're still just talking covalence, so we don't need to worry about it. But what it means to be a polar covalent bond is when somebody is winning. Okay, you can see on this picture down here that fluorine, the electrons are being pulled closer to it because fluorine is stronger when it comes to electronegativity or how much it wants to gain those electrons. Okay, and so if you have a polar covalent bond, what you need to remember is that that means there is an unequal distribution or sharing of charge. One atom is able to pull the electron closer to it due to having a higher electronegativity value. Okay, and so you can imagine this chocolate bar, some for me and some for you, it's not shared evenly. Okay, this picture of hydrogen chloride, both nonmetals, so they will share, but they don't want to share. Okay, spoiler alert, covalent compounds, they don't want to share their electrons. The issue is that you have 2 atoms that both really want electrons, so they start playing that game of tug of war. In this case, hydrogen wants an electron pretty bad, but chlorine wants it just a little bit more, so it's going to pull those electrons closer to it, making what is called a polar covalent bond. Okay? The way to remember this is that phrase polar opposites. If I have a polar covalent bond, I have opposite ends of my molecule or my bond. In this case, hydrogen is losing out on the electrons just a little bit, so it's going to be a little bit positive, and chlorine is pulling the electrons closer to it, so it's going to be a little bit negative. Question in the chat, are they growing? No, the reason it looks like they're growing whatever in these pictures is because chlorine is a bigger molecule or a bigger atom than hydrogen. You want to remember hydrogen's very little, teeny tiny small, and chlorine's just automatically bigger. Okay, if I looked up fluorine and chlorine, they're closer in size, but fluorine is still stronger, and so it's going to pull those electrons closer to it. The only example that's coming up is hydrogen chloride. Okay, But no, they're not growing or anything. It's just the electrons are being pulled closer to one atom compared to the other. Okay? Good question, Hugo. Is the bigger element always the one that is stronger? Not necessarily. Okay, if you look at electronegativity values, you'll see that in a period, the bigger element is stronger in terms of electronegativity, but the lower members in the group have lower electronegativity. And it has to do with this concept of electron shielding, which we're not going to have time to talk about in class today, but if you want to stay at 2:15, I'll explain it, okay? It's a pretty quick thing I can explain, but it doesn't fit in, so I'll explain it at the end of class, okay? Good questions. So if a polar covalent bond is an uneven sharing of electrons, what do you guys think a non-polar covalent bond is? That's the only word that you guys probably had never heard of in the learning target today. What do you think a non-polar covalent bond is?
Equal distribution.
You got it, okay? And so a non-polar bond is going to have an equal distribution of charge. Your two atoms are equally matched for each other in this game of bonding atomic tug of war. Okay, you can think of it, if any of you guys do martial arts like karate, Muay Thai, kickboxing, UFC, whatever, there's always a weigh-in at the beginning to make sure that the two fighters are evenly matched. That's going to lead to a non-polar covalent bond where everybody is sharing the electrons right equally in the middle. And this because nobody's strong enough to completely pull it towards it or take it away to make an ionic bond. Okay? And the quickest way you will know you have a nonpolar bond is if you have two atoms of the same element bonded to each other. Chlorine atoms here, chlorine atoms on the sun, chlorine atoms in the stars. I don't think there's any chlorine on the sun, by the way. They all have the same electronegativity. It's like 3.2 or something. You can look it up. And so they'll always be sharing electrons evenly because they're evenly matched. Okay? Another example, if you guys breathe in, you're breathing in diatomic oxygen, which is two oxygen atoms sharing 4 electrons equally because the two oxygen atoms have the same strength or desire to take those electrons away. Okay? Good work, my friends. Let's do a little check-in question. Using the drawing feature, please match the description to the term with a line. We have polar covalent bonds, non-polar covalent bonds, matched to either even or uneven sharing. Okay, I'll give you guys about 30 seconds. I'm still going to try to find... Okay? But in reality, we are not really going to be talking about bond polarity that much because it's a little bit small for us on the human scale. Okay, if we look at our answers, most of us drew a little X shape. Somebody went a little bit rogue and went around, but most of us did in fact get this correct. Where polar opposites is going to help us remember that there's opposite ends, meaning an uneven sharing of electrons. Okay, and then a non-polar, there's no north and south, there's no top and bottom. They are an even sharing of electrons. Okay, beautiful. So if you would like this slide, it's kind of a summary of everything we just learned. You can either screenshot it or it's already in your Unit 3 slides that you can look at later today. Okay, excellent. So now we're going to talk about the whole molecule. Okay, and this is because this has more kind of automatic implications for us on the human scale of the world. We're going to see it in action in our lab tomorrow and the next day. And so the concept of polarity is still the same. Polar is uneven, nonpolar is even. But we're looking at whole molecules, meaning whole covalent structures. And so what we're going to be looking at is their shapes and, more importantly, their symmetry. Okay, and so here you can see an example of a polar molecule down here at the bottom where you have an unbalanced distribution of charge throughout the whole thing. You are going to know this very quickly just by looking at the shape. Here I have an asymmetrical shape where if I cut it in half top to bottom, yes, I see the same thing on both sides, but remember we want at least 2 planes of symmetry. So I'm going to cut it in half horizontally, and you'll notice we have a difference on the top versus the bottom. Okay, and so in the bottom here I have a hydrogen bonded to nitrogen, but on the top I have 2 lone pair electrons. Those lone pair electrons are like pure negative charge. And so that's going to make this end of the molecule a little bit negative, and then hydrogen, lower electronegativity, a little bit positive. Okay, and if you have something with a positive and a negative end, you basically have mini magnets. So you guys remember when we talked about charge, I showed you my little water molecule magnets, and I told you they weren't just decoration in my nerdy house. There was a reason for them to be magnets. This is the reason, okay? A nonpolar molecule, exactly the same thing as a nonpolar bond, except over the whole molecule, you will see an even balanced distribution of charge, and you will know this is the case if you have a perfectly symmetrical shape. Okay, meaning if I cut it in half top to bottom, I see the same thing on both sides. And intro chem, cut it in half side to side just to be sure. Make sure you see the same thing on top and bottom. Okay, in reality, these are three-dimensional structures, so if you continue this topic in college, you'll learn more about it. But for Regents Chem, top to bottom, side to side, make sure you see the same thing on both sides. Okay, so let's do a little check-in. How the heck am I going to remember all this, Miss Garcia? Well, Miss Garcia showed us our lovely Ugly Sweater Day sweater from the holidays, and I said there was a chemistry joke in here. Oh, snap. The word snap, my friends, is going to help you remember some things about this. So what do you think snap is going to help us remember in terms of molecular polarity? I'm going to give you guys about 30 seconds to think about it. You can type your answer in the pear deck. I don't expect very many people, if any, to get this. Maybe don't think about the word snap itself, but maybe the letters that make up the word. So this is going to help us with molecular polarity. Some people are just putting science words. Oh, we have a winner. Somebody got it. All right, one of your classmates did in fact get it. The word snap can help us remember what it means to be a polar molecule or a nonpolar molecule, and that snap is spelled S-N-A-P. Otherwise, could stand for symmetrical is nonpolar and asymmetrical is polar. If you look on over at the screen share, one of your classmates got this here. It is an acronym that can help you remember that if you have a symmetrical molecule, you can remember that it is nonpolar, like my nonpolar bear here with two heads, and an asymmetrical is going to be polar, just like a polar bear has a head and a tail. Okay, they have opposite ends. Okay. If I show you two examples, here is chlorine again. Chlorine is a perfectly symmetrical molecule. Cut it in half, top to bottom, side to side. We see the same thing on both sides of the planes of symmetry. And symmetrical, SNAP, SN, symmetrical is nonpolar. And so we will know that this is a nonpolar molecule. Okay? But the one molecule that you have to kind of essentially just memorize is our dear friend dihydrogen monoxide, aka water. You will notice that anytime I have drawn a water molecule, it is always bent like this. You will also notice my lovely little Mickey Mouse type shaped thing. This is essential to water's characteristics and water's ability to provide life. Okay, you guys should know that when people go to other planets, the first thing they look for is signs of water as a sign that there could be life on that planet. Because water molecules are asymmetrical, if you cut them in half side to side, we have two pairs of electrons on the top and two hydrogens on the bottom, making this a completely polar molecule. Water molecules are polar. They behave essentially like little magnets with positive and negative ends. And if water molecules did not do that, life as we know it would not exist. Okay, we'll talk more about how water's polarity leads to it being the structure of life in February, but this is very important to remember that water is polar. This is going to be our guiding force in our lab tomorrow, but I do want to be respectful of time. I do have two more check-in questions that we can do together, which you can stay and do. I'll also explain electron shielding for anybody who's curious, but your asynchronous work on Google Classroom should have posted. If you look on the classwork tab, it is a quick 10 question quizzes, which is essentially going to just ask you to go through, is this molecule polar or nonpolar? Some of them you have to draw, some of them I gave you the picture. Okay? So if you feel like you have a good hang on it and you feel like you've got this, feel free to depart our Zoom call. But if you want to do 2 more check-in questions, one of them is on your pair deck now, which you can try. Otherwise, I will see you all tomorrow, okay? So if you're leaving, goodbye. If you want to stick around, feel free to do so. I can explain electron shielding or go through a few more questions, okay? Goodbye, Anthony.
Bye, Miss. Goodbye, Miss.
Goodbye. Have a
Goodbye,
good
Bye, Miss.
Joshua.
day.
Goodbye,
Bye,
all.
Karma. Bye,
Goodbye.
Joshua.
Goodbye, Karma. Goodbye.
Bye. If you are sticking around and doing the check-in question on the pair deck, which of these molecules is polar? You're going to check symmetry, and you're also going to remember SNAP, S-N-A-P. A symmetrical molecule will be nonpolar.
The first one.
AP, an asymmetrical molecule, will be polar. So, because we're looking for a polar molecule, we are looking for an asymmetrical, meaning not symmetrical molecule. Okay? So you can drag your check mark for anybody who's still sticking around. And if we look at our responses, most of us think this one with the H's and the O's is polar. So let's check with the other ones. This red and gray one is actually an image of carbon dioxide. If I cut this in half horizontally, I see a red circle with 2 lines, a red circle with 2 lines, so it looks the same. And then you have cut it in half vertically, we see the same thing on both sides. So this one, carbon dioxide with the red and the gray, is perfectly symmetrical, and SNAP, symmetrical, is non-polar. Okay? Similarly, with CH4, no matter where you cut CH4 in half, it looks the same on both sides, making it symmetrical, SNAP. Symmetrical is non-polar, asymmetrical is polar. And so this answer from one of your classmates is correct. This is water. It is the only polar molecule on this screen. Hugo, I remember the difference between polar and nonpolar by using fiction and nonfiction, showing that non is the opposite, and so would this be? Yeah, good. Whatever you need to use to help you remember, use it. It is kind of annoying that the word polar is uneven and the word nonpolar is even. It would be nice if the two with prefixes would match, but you know, I don't make up the rules. So. All right, let's do